Welcome class, this is Tim Tomlanovich. We're in water technology. Welcome to Learning Plan 4. Okay, so Learning Plan 4. Oops. Okay, here we go. Gravity flow. Let's talk about gravity flow. Water flowing in a pipe or channel with a free surface exposed to the atmosphere is termed open channel flow or gravity flow. A pipe flowing full but under atmospheric pressure is also open channel flow. So sanitary sewer, stormwater. So if it's still flowing full, but it's open to the atmosphere on each end, which sanitary and storm sewer typically is, it's called open channel flow. So, however, there are some pipes in which wastewater is pumped under pressure, and those terms are called force mains. So, when you look at sanitary, they can only go so deep because of gravity flow, so they can only go so deep, and then they have to pump the water up to an elevation and allow the gravity to take over again. So again, it's exposed to the atmosphere. So water lines are not open channel flow. Those are pipes under pressure. So that was where Hayes and Williams equation came in from the last learning plan. So when designing storm or sanitary sewers systems, we assume that the discharge, the flow rate Q, is constant with time. We also assume that the slope of the water surface and cross-sectional flow area are constant. So the slope is that hydraulic grade line. Remember me talking about that? And the cross-sectional flow area are constant. So we're assuming we have to make some assumptions to make some design assumptions to make our design work. So in reality, that is not true, especially when you look at stormwater. There's probably a constant small steady flow going through there, but when it rains, it all of a sudden it increases, then it decreases again. The same with sanitary sewer. Okay, so when the previous assumptions are made, the condition is termed steady uniform flow. So when you hear that steady, or they call it steady state uniform flow, so that's what that means. So the cross-sectional area is constant and the water surface is constant. Okay. So, terminology of gravity flow, cross-sectional flow area. So that is literally what you see here in blue. So let me so basically I am highlighting what you see in blue here that is my cross-sectional area of flow. My crown of my pipe is the underside inside diameter of the pipe, not on the top, inside diameter. The wetted perimeter, okay, as you can see, is literally is where the water only touches the walls of the inside of the pipe. That is my wetted perimeter, okay? And then my invert elevation is basically on the inside. Obviously you can't see that, so let's do a blue. So my invert is right there. Inside of the pipe, bottom of the pipe, inside diameter. Crown is in the top. Cross-sectional area of flow is literally the flow area, not the cross-sectional area of the pipe, just the flow. So if the pipe is full, that means my cross-sectional area of the pipe will equal the cross-sectional flow area. Okay, so this is some terminology. So how do we calculate gravity flow? It's something called Manning's equation. So this is in our English units. Q, which is discharge in cubic feet per second, equals 1.5 divided by N. N is the roughness coefficient, times area. A is the cross-sectional flow area. So area equals cross-sectional flow area of just the water. Okay, don't get that confused. Times the hydraulic radius raised to the 2/3 times the slope of the channel bottom raised to the 1/2. Okay, so slope is feet over feet, meters over meters. It's a unitless number. Okay, we'll go over hydraulic radius on the next slide, and then if we look at number, area is the cross-sectional flow area. So English, they're all the same except this constant here is 1.9. Okay. I'm sorry, this constant is 1.0. So Q is in cubic meters per second. N is a roughness coefficient. That's a unitless number. A is cross-sectional flow area, meters squared. Hydraulic radius, meters. Slope of channel bottom. Okay, metric. All right, let's talk about the R terms. Hydraulic radius, cross-sectional flow area, A. Okay, if you, oops, let's erase that. Area divided by the wetted perimeter. So I have square feet divided by perimeter is feet, I get feet. So the wetted perimeter again is just the surface touching the inside wall of the pipe. And the cross-sectional area of the flow is this. Okay. So how do I calculate the perimeter of a circle? If you remember, that is pi times d is the circumference of the circle. Area is pi d squared over 4. Okay, wetted perimeter. So hydraulic radius, cross-sectional area of flow divided by wetted perimeter. So some terminology there. Okay, here's the metric. So we have meters squared divided by meters, same principle. Roughness coefficient. So these apply to both English and metric. So roughness coefficient, if you think about it, the smoother the pipe, the more flow we get. So when you look at water sheet flow, so if it's a smooth plastic pipe, it's going to flow fairly fast. But as soon as it gets rougher and rougher, the friction is going to want to slow that flow down. So each pipe has a different, or each kind of material has a different kind of roughness coefficient. So if you look at concrete, 0.13, in earth and weeds, 0.35. So if you look as the surface gets rougher, when that water has to travel over that surface, the Manning's roughness coefficient goes up, and that will, okay? So different Manning's coefficients. All right, let's work examples 216, 217, and 218 in your book. Okay, I'll read these problems out to you. So let me get my pen going here. So problem 216, a rectangular drainage channel is 3 feet wide and is lined with concrete, as illustrated in figure 2.20, which you're seeing on your screen right now. The bottom of the channel drops an elevation rate of 0.5 feet per 100 feet. What is the discharge in the channel when the depth of water is 1.5 feet? Assume n equals 0.13. Okay, so if we look here, first let's write down, so are we in English or metric? We're in English. So let's write down our equation. Q equals 1.5 divided by n times cross-sectional area of flow times the hydraulic radius raised to the 2/3 times the slope raised to the 1/2. Okay, so n is concrete, and they tell us is 0.013. Area equals cross-sectional flow area. So if we go back to this picture, our cross-sectional flow area is, so the flow height is 1.5 feet and the flow width is 3 feet. So our cross-sectional area of flow is 1.5 times 3 feet. Okay, so if I look, this where I'm shading green is my cross-sectional area of flow. Okay, so 1.5 times 3 feet. They're both feet, okay? Equals, so if I multiply that out, 1.5 times 3, and I get 4.5 square feet, okay? My hydraulic radius equals cross-sectional area of flow divided by my wetted perimeter. So we know this term is the same. All three of these are the same. Cross-sectional area of flow, okay? So figure out hydraulic radius, it's the same value. So we use 4.5 square feet divided by, now what is our wetted perimeter? Remember, it's the water that's only touching the walls. So we have 1.5 feet plus 3 feet plus 1.5 feet. So 1.5 plus 1.5 is 3, plus 3 is 6 feet. So I have a wetted perimeter of 6 feet because it's a square channel. So we divide that by 6.0 feet, 4.5 divided by 6.0, I get 0.75 feet. Okay, my slope, they're telling me in the problem, the elevation drops at 0.5 feet per 100 feet. So 0.5 feet divided by 100 feet, and that equals, basically I moved the decimal place 2 spots, 0.005. That's a unitless number. So I've just defined all my terms. So now we can go in and figure out our flow rate of that open channel. Q equals 1.5 divided by 0.013 times 4.5 square feet. Sorry, this isn't cubic feet, this is square feet. Okay. Times 0.75 raised to the 2/3 times 0.005 raised to the 1/2. Okay. So you got to do order of operation. I'll talk you through this. So 1.5 divided by 0.013 equals, so what I like to do is, so this is 1115.38 times 4.5 times, so 0.75, what I'm doing is I'm figuring out each of these terms. 0.75 raise, make sure you put the 2/3 in parentheses, 2 divided by 3 parentheses, so I'm raising 0.75 to the 2/3, and that is 0.667 times 0.005 raised to the 1 divided by 2. Make sure that's in the parentheses. Hit equals times 0.999. Okay, and that equals, so 115.38 times 4.5 times 0.667 times 0.999. I get 345.9. And obviously I did something wrong here because my answer is not matching the book. 1.5 divided by 0.013 equals, oh, that's why, times 4.5 times 0.75 raised to 2 divided by 3 equals times 0.005 raised to the 1/2. So my calculator is going goofy here, so we should get, so ignore these. So having your calculator here, you can put this all in at once, and I get 30 cubic feet per second is my flow rate. Okay, so that's how you do a rectangular channel, wetted perimeter. Okay, so that was example 2.16 in the book. So again, write down your equation, write down the variables that they tell you, or you got to calculate each of these variables, plug it in the equation, and you calculate your answer. All right, 2.17. A 12-inch diameter pipeline is built on a 1% slope. Assuming n equals 0.013, determine the discharge capacity of the pipeline with full flow. What is the flow velocity? All right, first thing you do is you write down your known variables. Okay, so we know we have a D equals 12 inches. We have a 1% slope. Slope equals 1%. So I divide by 100, and that equals 0.01. Okay, because you take 1, because remember it's a slope, 1 divided by 100, 0.01. Okay. And it says, determine the discharge capacity of the pipeline with full flow. Diameter of full flow. So we need Q full. And what else is it asking us? It is, what is the flow velocity? V. V. It's asking us V. Okay. All right. So I'm going to show you how to use the nomograph here, and then we'll put these numbers actually into the equation. Okay. So how do you work this? So if you look here, so I'm going to use my ruler here. So the book kind of shows you, but I'll talk you through this. So I'm going to use a red pen. All right, so, okay, I have discharge over here. So that's what I'm looking for, discharge, okay, cubic feet per second. Okay, if I look over here, I have slope, slope percent, velocity, velocity, and then here's my Manning's roughness coefficient. Okay, so we know N equals 0.013. Okay, so what you do is we know N equals 0.13, okay, and we know the slope. Slope is 1%, and we put that there, okay? So then you draw this line. So you need to know 2 out of the 3. Okay, I connect those 2, and they call this the turning line. So once I know the turning line, then I know my pipe diameter is in 12 inches. I know that's right there, okay? So now, if I go here, I go through there, and then I look at where my discharge is. and I run through 4 discharge cubic feet per second. This is 4, so I run through 4. This equals 4 cubic feet per second. Okay, now it's asking us, so that's how much when the pipe is full. This nomograph works when the pipe is full. Now it's asking for velocity. Okay, so now you go back to the turning line here, and then you project the term back here, and then you run into the velocity line. So 4 point, that's 4, that's 5, so looks like about 4.5 feet per second. Okay, so now let's plug this information into the Manning's equation to see what see how close we come to our answer. So that's using the nomograph. Okay, so now we know Q equals 1.5 divided by N times cross-sectional flow area times hydraulic radius raised to the 2/3 times slope to the 1/2. 1.5 divided by N, which is 0.013, times cross-sectional area of flow. So that is pi d squared over 4, right? That's the area of a pipe when it's full. So pi. So what does that need to be in? Does it need to be in inches or does it need to be feet? So feet. So we go pi. Find my pi here. Arg. There it is. Pi times 1 foot squared divided by 4. I get 0.785. So 0.785. Okay, that's feet squared times hydraulic radius. So hydraulic radius equals cross-sectional area of flow over wetted perimeter. Now, if you look in your book, if the pipe is full, because we know this is pi d squared over 4 divided by pi times d, if we cancel terms out, we end up with d over 4, which is nice. So 1 divided by 4 is 0.25. So this is a really handy, so when a pipe is full, you can use d over 4 because of the way it turns out. 0.25 raised to the 2/3 times my slope is 0.01 raised to the 1/2. Okay? All right. 1.5 divided by 0.013 equals times 0.785 equals times 0.25 raised raised to the 2/3 times 0.01 raised to the 0.5. And I get 3.59. So I get 3.59 cubic feet per second. So when you look at the equation, it's going to be more accurate. So I get 4, I get 3.59, 3.64 when I look at the 2. So now velocity we know equals Q over A, because remember Q equals velocity times flow area. I rearrange that equation. So I have a Q of 3.59 cubic feet per second divided by my area, 0.785 square feet. So 3.59 divided by 0.785, and I get 4.6 equals 4.6 feet per second. Pretty close to the same answers. Okay. So there we go. There we go. And using, see how quick the nomograph was? So you should be able to do both. Okay, that was 2.17. Let's do 2.18. All right, a 450 millimeter diameter storm sewer. Okay, 450 meters, so D equals 450 millimeters with an N value, a Manning's roughness coefficient of 0.13, that's a unitless number, is built on a grade of 2%, slope equals 2%, or 0.02. I turn that into decimal form. What are the discharge capacity and velocity of the flow when the pipe is full? So Q full and V full is that the questions they're asking. Okay? So let's do the nomograph. So D 400. So let's go back to the equation. All right. Cross-sectional area has to be in meters squared. Okay. In meters. In a slope. So we got 1, and then our flow is cubic meters per second. So we need to make sure this D is in meters. 0.450 meters. 1,000 millimeters per meter, move that decimal place back 3 spots. Okay. So let's go look at so we know we have a diameter. So let's start tagging things we know. Diameter of pipe. So if you look here, diameter of pipe here says centimeter or inches. So that is 45 centimeters. So just be careful to look at what the units are providing on the nomograph are different units than what's required for the equation. So you got to switch back and forth. So there's 100 centimeters per meter. So I get 45 centimeters, 450 millimeters, or 4.45 centimeters, right? Is that, yeah. So 450 divided by 100. I'm sorry, that's 4.5. I knew I was doing something wrong there. So that is 4.5 centimeters. 1, 2, 1, 2, 3. Okay. So we have 4.5 centimeters pipe diameter. And I just want to make sure I'm reading the problem right. 450 millimeters. Centimeters. So we cannot use the nomograph here because we don't have a pipe diameter of smaller, as you can see here, 450 divided by 100 is 4.5 centimeters. So we don't have anything 4.75 meters. So we cannot use the nomograph here. So that means we got to just use the equation. Okay. So Q equals 1.0 divided by 0.013 times cross-sectional area of flow. And again, that is pi d squared over 4. And that equals pi. Now we have to be in meters. 0.450 meters squared divided by 4. And that equals 0.450 squared times pi divided by 4. I get 0.159. 0.159 meters squared times d over 4. So that is 0.450 divided by 4. And we raise that to the 2/3 because the pipe is full. 0.45 divided by 4. That's 0.1125. 0.1125 raised to the 2/3 times my slope 0.02. It can't be in percent. It has to be in a decimal form, unitless decimal form, raised to the 1/2. So Q equals 1.0 divided by 0.013 times 0.159 times 0.112. Oops, I gotta start over. 1 divided by 0.013 times 0.159 times 0.1125 raised to 2 divided by 3, okay, times 0.02 raised to the 0.5. And I get approximately 0.4 cubic meters per second is my flow. Okay, and then V equals Q over A, and that equals 0.4 cubic meters per second, and I divide that by my area, 0.15 meters squared, and I get divided by 0.159, and I get 2.5 meters per second is my velocity full. So this is full pipe. Okay, so unfortunately, as you can see, we couldn't use the nomograph because our pipe diameter is too small. Okay, so you have to go to the equation. So okay, so now what we're going to do is we're going to find, how do we find the area, cross-sectional flow area, and the wetted perimeter of a pipe flowing partially full. Okay, because it's not full, we got part of a circumference and part of a cross-sectional area. So there, guess what? We have a chart right here. So if you look here, the key to, so this is partially full. So we cannot use the area, the entire area of that pipe and figure out the cross-sectional area of flow because it's not full. So we have part of it. So they created this chart for. So the key to this, if you look here at this chart, we have a ratio little q over big Q or little v over big V. Okay, Q, so no matter what, Q equals full. So the first thing you need to do to use this equation is you need to find Q full. And you can do that using the Manning's equation. Okay, you assume the pipe is full. Assume pipe is full. Okay, you calculate Q, because then you can, if you know this guy, you'll be able to find this guy based on little d, partial depth, look down here, d over big D. So once I know, so example, if I know my ratio of partial diameter to full diameter, and I come over and I hit my discharge curve of Q and I come down, I end up with a Q, little partial flow over big Q. That's a ratio, and then I do algebra, then I can find my partial full. So no matter what, you have to find my flow when its pipe is full, and my same thing with V. Big V equals Q over A, full. Okay, so that's the key to this chart. And then if I'm finding flow, I got to make sure I hit the flow curve, and if I'm finding velocity, I got to make sure I hit the velocity curve and use the ratios. Okay, so that's the key to this. All right, so let's do 2.1, 2.2, and 2.3. Example 2.21. A 300 millimeter diameter pipe. Okay, write down what you know. D equals 300 millimeter diameter pipe with an N value, or Manning's roughness coefficient, 0.013, is constructed on a slope of 0.2. S equals 0.02. What is the depth of flow in the pipe when it carries a flow of 96 liters per second? What is the velocity of flow at depth? Okay, so what is the depth of flow? So it's asking me for the depth of flow, partial flow depth, little d, okay, when it carries a partial flow, little q, of 96 liters per second. Okay, so step one. So step one is find Q full when we assume the pipe is full. So we're in the metric world, so 1.0 divided by 0.013 times my cross-sectional area of flow. So remember, the pipe is full, so pi d squared over 4. Remember, we have to be in meters when we're using the equation. So 0.3 squared times pi divided by 4. I get 0.071 meters squared times hydraulic radius is d over 4. So that is 0.3 divided by 4, and that is 0.075. 0.075 meters, and we raise that to the 2/3 times my slope is 0.02, and we raise that to the 1/2. So that's our first step. So 1 divided by 0.013 equals times 0.071 equals times 0.075 raised to the 2 divided by 3 equals times 0.02 raised to the 0.5 equals. So I get 0.137 cubic meters per second. Okay? So if you're wondering how this Manning's equation actually came about, they do full scale load tests, and they did a lot of research here. So, okay. So now I know Q full. So now I can find step 2. Let's find the Q, or let's calculate the little q over big Q ratio. So we know it is 96 liters per second times 1 cubic meter equals 1,000 liters. Remember, we got to be in the same units. So 96 divided by 1,000. We move the decimal back 2 spots. So that equals 0.096 divided by 0.137. And we get our ratio divided by 0.137. And that is 0.7. that equals little q over big Q ratio. Okay, so now we go find that right here. Here's 0.7. Okay, so now let's grab the ruler. So I know Q. So if I gave you a velocity, you'd have to go to the V curve, but you know Q full. Okay, so I go up to the discharge curve. Okay, and then I come over here. Okay, so I know, so my ratio of D over big D equals, I'm going to say 0.62. Okay, so now we know we got to find little d. So we can take 0.62 times my my diameter of my pipe, and that equals 0.62 times 0.3 equals 0.62 times 0.3, and that equals 0.186 meters, or is my depth of flow, D, or 186 millimeters. Okay, so I solved that equation. Okay, is there anything else they're asking me? Okay, what is the velocity of flow at that depth? Okay, so now so at a flow depth, because if you see here, here's our flow depth right here of 0.186 meters. What is the velocity at that flow? Okay, so now if you look here, if you come back up here to the chart, we can basically, what we do, we come over to the velocity curve and we come down. Okay, and then I get my little v over big V ratio, and I'm going to say 1.09. Okay, so basically 1.09 times my velocity flowing full will equal my partial velocity at a depth of 1.186 meters. So, but first I need big V, my velocity full. So step 5 equals Q full divided by cross-sectional area. And that is 0.137 cubic meters per second divided by my area, which is 0.071 meters squared. 0.137 divided, 0.137 divided by 0.071, I get 1.93 meters per second equals V full. So this equals 1.09 times 1.93 meters per second, and that equals times 1.09 equals 2.10 meters per second. Okay, now I want you to notice something. So my velocity of the pipe flowing full is 1.9 meters per second, but at a partial height of 0.186, it's actually 2.10. Interesting, isn't it? Reason why that is, if you look at these curves here, okay, if you look at the curves here, So like you say, the Q, V over V or Q over Q, that should equal 1, right? But if you look here, our velocity is actually faster because we have less friction. We don't have this friction against the sidewalls of the pipe. So actually, believe it or not, we can get faster flow in partial full pipes than full pipes because of the less friction against the inside pipe diameter walls. Okay. So very interesting. So something to keep in mind when you look at that chart. Okay. Okay, did we answer all the questions? We found little d, which is 0.186. We found partial velocity, 2.10 meters per second. All right, example 2-22. What is the maximum possible discharge capacity of a 900 millimeter diameter pipe with an N 0.013 built on a slope of 0.1%? Okay. So maximum possible discharge capacity. Maximum discharge capacity. That doesn't necessarily mean Q full. So Q is just from the previous example, we notice sometimes we can get more flow from a partial flow than a full flow. Oh, that's a tongue twister. Q maximum. Okay. So D equals 0.900 meters or 900 millimeters. N equals 0.013. And our slope equals 0.1. Okay, do I have enough information there to find Q full? Yes. Yes, I do. So what is the maximum discharge of a 900 millimeter diameter pipe? Okay, so if I look here, let's look at the curve here. Where's the curve peak out here? It peaks out right there. Okay, so if I take my ruler, it peaks out right there. Okay, so if I bring that down, I'm gonna have to say, okay, my Q over big Q equals 1.09. Okay, and then if I look over here, I have, just for sakes, my D over D is my partial depth divided by my full depth. I'm going to say is 0.94. Okay, so do we need Q full? Yes. Okay. All right, so we can do the Manning's nomograph or we can do the equation. So I'm going to do the equation because we need practice doing the equation. So Q full equals, all right, so 1.0 divided by 0.013 times the area, so that's pi d squared, so 0.9 squared times pi divided by 4, and that equals 0.636 times my hydraulic radius. So that is 0.9 divided by 4 is 0.225. Because remember, it's D over 4. It's cross-sectional area of flow divided by wetted perimeter. Because the pipe is full, we know it equals D over 4. So just remember that. Okay. Remember what hydraulic radius is. It's that definition. Raised to the 2/3 times, and my slope was 0.1%. So that is 0.0012 raised to the 1/2. So my flow is 1 divided by 0.013 times 0.636 times 0.225 raised to the 2/3 times 0.001 raised to the 0.5. So I get 0.572 cubic meters per second when it's full. So Q max, oops, sorry. Where's my view? There we go. So it's a partial flow. Q max equals Q full times 1.09. So that is 1.09 times 0.572. So equals 0.623 cubic meters per second. So that is our first answer, because the question is asking, what is the maximum possible discharge capacity of a 900 millimeter diameter pipe? So I answered that. So, and what, we can go even further with that. What's our partial depth? D equals partial depth divided by full diameter times equals my ratio of 0.94. Your book says 0.93. So partial depth equals 0.94 times 0.9 meters. 0.9 times 0.94. So 0.846 meters equals partial depth. So basically, again, what did we do? We looked where the Qmax curve went. So you can do the same thing for the velocity too, right? So we always have to find Q full. So our maximum flow capacity of a 900 millimeter diameter pipe is 0.623 cubic meters per second at a partial depth of 0.4846 millimeters or 846 millimeters. So it just shows you that pipes flowing full don't necessarily mean maximum discharge. So that was 2-22. Last one, 2-23. And then this will be it. Then you can do your homework and then you can do the quiz. Okay, an 18-inch diameter sewer line. All right, so D equals 18 inches, which equals 1.5 feet. With a Manning's roughness coefficient of 0.013. Now this is concrete. Obviously, you can use this for any other surface. Drops 1.6 feet in elevation over a distance over a 400-foot distance. So slope equals 1.6 feet divided by 400 feet. So our slope is 1.6 1.6 divided by 400, 0.004. Okay. Determine the discharge and velocity in a pipe when the depth of flow is 6 inches. So, partial depth, small d, equals 6 inches, which equals 0.5 feet. So it wants us to find partial Q at that depth and partial V at that depth, small v. So, okay. So first thing you need to do is find Q full. Equals. So we're back into English metrics, English units, I should say, 1.5 divided by my Manning's coefficient, roughness coefficient, times the area of my pipe, cross-sectional area of my pipe, 1.5 squared times pi divided by 4 equals, let's make sure that's correct, 1.5 squared times pi divided by 4, 176.7 square feet times my hydraulic radius. Remember, it's the cross-sectional area of flow divided by my wetted perimeter. So the wetted perimeter, and when a pipe is full, is pi times d. The cross-sectional area of flow is the same as the area of the circle. When you divide those two out, it actually ends up being diameter divided by 4. So just don't forget about that. Okay. So my diameter is 1.5 divided by 4, and that's 0.375. Okay, and that is raised to the 2/3. And then when you put it in your calculator, make sure you take 2 divided by 3. Your answer will be a little more accurate than rounding that to 0.67. Times my slope of 0.004 raised to the 1/2. So let's figure out our flow when it is full. 1.5 divided by 0.013 times 176.7, that's the cross-section area of flow, times 0.375 raised to 2/3 times 0.004 raised to 0.5. And I get 670.5. I'm going to say 671 cubic feet per second. You could also pull this off of the nomograph too, because you know your diameter, you know your slope, you know your Mannings, you can do that, okay, to find Q full. But I prefer, it's just easier sometimes just to find that. Okay, so let's find now, so that's step 1. Step 2, let's find our partial depth divided by our full depth, and that equals 6 inches. So as long as these units are the same, you can take 0.5 divided by 1.5, or you can take 6 divided by 18. Doesn't matter, because it's a unitless number. And that equals 6 divided by 18, 0.333, 0.33, whoa, 0.33. Okay, so if that's my ratio of partial depth over flow depth, so let's go find that on our chart. 0.333, somewhere right around there. Okay, so we're looking for partial Q and partial V. So what we need to do here, let's grab a ruler. 0.333. I'm going to say it's right about there. And basically, because I need velocity and flow, so first one I'm going to hit the Q curve, the discharge curve, because that is my discharge ratio, and then I also have to go to the velocity curve to find my velocity curve. So you got to do it twice, basically. Okay. So now we know Q partial at 6 inches equals, so my discharge curve, wasn't quite perpendicular, 0.23 equals 0.23, which equals number Q over big Q curve, and then I take 0.23 times my Q full, and that equals 0.23 times 671, and that equals 671 times 0.23, and that's 154 cubic feet per second. I'm just rounding. Okay. So that is the discharge at a depth of 6 inches in that pipe. So now the velocity is, we get 0.82, which equals partial velocity over full velocity. So we got to take 0.82 times v, the full velocity, and that equals 0.82. I did not calculate my full velocity. So this is step 3, this is step 4, step 5. V full equals Q full divided by area, and that is 671 divided by 176.7. 671 divided by 176.7, and that equals 3.8 feet per second. Okay, so times 3.8, so that's 0.82 times 3.8 equals 3.1 feet per second. So that is my partial velocity at a depth of 6 inches in a 18-inch diameter pipe. So answer. So let's see how close we got to the book. I get 3.1. My Q, oh, they're in gallons per minute, but you can convert that because they use the Mannings. The Mannings, you just got to convert it back into cubic feet per second. So remember, there's 7.48 gallons per 1 cubic foot. So I get the same answers, except they get 0.22, 640 gallons per minute, which is probably equal to 154 cubic feet per second. So make sure you go through these example problems and you understand how to do them and how to use this chart. Okay, so that is the end of this presentation. Your homework is in Blackboard under Learning Plan 4, and I will be posting the quiz shortly. So thank you for your attention.